Hey everyone, and welcome back to this class, Artificial Intelligence, Reinforcement Learning in Python. In this lecture, we are going to look at the Bellman equation by example. Now, of course, in the real world, you may have thousands or maybe even millions of states. But in this lecture, we are going to look at some very simple models with just a handful of states, and you'll see how we can solve the Bellman equation by hand for some very simple cases. Hopefully, this helps you gain some intuition about the Bellman equation and realize that it's not so scary. And also keep in mind, just from a big picture perspective, this idea of solving for v of s, that's essentially what this entire course is about. This whole thing can be generalized to this idea. We have a model called an MDP, and there's this value function v of s. Now, all we need to do is find it. It's really that simple, so once you've handled the details, you can take a step back and appreciate this general framework and how useful this abstraction is for solving a variety of problems. Let's start with a very basic example. We have two states, start and end. The probability of going from start to end is 1. So every time you play this game, it's completely deterministic. Every game just consists of 2 steps, start and end. Let's suppose the end state gives you a reward of 1 and the discount factor is gamma equals 0.9. The question is, what do we need to find? Now, if your answer was, we need to solve for the value function, that's great, you are on the right track. Since there are only 2 states, that means we need to find v start and v end. See if you can do this on paper before we move to the next slide. Now remember that the value is the sum of all future rewards. Since at the end state there are no future rewards, the value of the end state, or in more general terms, any terminal state, is always 0. Because everything else is deterministic, v start is 1. Why is this? Well, remember that you can think of this as a probability tree. So going from start to end is the only possibility, so the weight of that edge is 1. Note that we do not multiply this reward by gamma, because gamma applies only to future states. So the full equation is actually r plus gamma times v end, where the second term is just 0. For our next example, I'm going to add a third state. Note how everything is still deterministic. Therefore, every game just has 3 steps, start, middle, and end. The reward again is 1 for arriving in the end state and 0 otherwise. Gamma remains as 0.9. As you already know, our job is to find v start, v middle, and v end. So see if you can do this on paper before we move to the next slide. So because v end is a terminal state, we already know its value is 0. In this example, v middle takes on the role of v start from our previous example, so v middle is 1 by the logic we discussed previously. Since this is all deterministic, we can use the Bellman equation in simple form to determine the value of v start, which is r plus gamma times v middle, which is 0.9. In this next example, we're going to make things a little more complicated. We have the same states and everything is still deterministic, but now you get a reward of minus 0.1 for going to the middle state. Our job again is to find v start, v middle, and v end. See if you can do this on paper before we move to the next slide. So because v end comes after v middle, its value is unaffected and it remains as 0. And since v middle is only concerned with future rewards, its value is also unaffected, so it remains at 1. v start, however, is affected. It's equal to minus 0.1 plus 0.9 times 1, which is 0.8. Alright, so hopefully you're getting the hang of this. In this next example, we're going to introduce some randomness. Our states are S1, S2, S3, and S4. S4 is a terminal state, and you always get a reward of 1 when you go here. S2 and S3 both go to S4 100% of the time, so this part is deterministic. S1 goes to S2 50% of the time, and to S3 50% of the time, so this part is random. The reward for arriving in S4 is 1, and the reward for arriving in S2 is minus 0.2, and the reward for arriving in S3 is minus 0.3. Before we move on to the solution, this example introduces an interesting nuance. What does the probability I just mentioned refer to? If I say we have a 50% chance of going to S2 and a 50% chance of going to S3, what does that really mean? Because this is reinforcement learning and there are multiple components in an MDP, this is not just a simple coin flip. I don't flip a coin and go which way it tells me to go. I'm an intelligent agent, and therefore I have an internal policy that tells me what action to do. Importantly, it's not the probability of where to go, it's the probability of what to do. But if you recall, this is not the only relevant probability. We also have P of S prime R given S and A. This just means that by doing some action A in state S, the result can be random. So if my action is flip a coin, of course there are multiple possible results. I may get heads or I may get tails. That's one way an action might result in a probabilistic next state. So when I say you have a 50% chance of going to S2 and a 50% chance of going to S3, that sounds really intuitive and simple, but it oversimplifies the MDP and results in some ambiguity, although when you verbalize it, it sounds simpler. For this particular example, let's assume P of S prime R given S and A is deterministic, and the 50% probabilities I mentioned earlier refer to the policy pi of A given S, where the action is simply just to go to the next state. That means the agent itself decides where to go by random chance, and it's not a result of the environment. So see if you can solve this on paper before we move to the next slide. So as usual, the value of the terminal state, V of S4, is 0. Everything that happens after you arrive in S2 and S3 is deterministic, and so it follows the same logic as the previous examples. So V of S2 is 1, and V of S3 is also 1. V of S1, however, must be calculated using expected values. So I have a 50% chance of going to S2 and receiving a reward of minus 0.2. I have a 50% chance of going to S3 and receiving a reward of minus 0.3. After that, the next state is always S4, which always yields a reward of 1, so that part can be effectively removed from the expected value. The value of S1 is then just 0.65, since it's just the sum of these two branches. In this next example, we're going to extend this problem just a little bit further. The expected value in the previous example was easy to calculate because you always ended up in the same terminal state S4. In this example, that won't be the case. Note that S1 can go to either S2 or S3, but from S2 or S3, we can end up in either S4 or S5. So now we have two terminal states and there are multiple paths to either one. The only relevant rewards for this example are a reward of +1 if we end up in S5, and a reward of -1 if we end up in S4. Again, try this on your own and we'll look at the solution in the next slide. Firstly, we know that V of S4 and V of S5 are 0, since they are both terminal states. Second, we can calculate V of S2 and V of S3, just from the rewards, since we know the next state must be terminal, so we don't need to use the full Bellman equation. So V of S2 is 0.8 times -1 plus 0.2 times 1, which is minus 0.6. Its expected value is negative because it ends up in the losing state more often. V of S3 is equal to 0.9 times 1 plus 0.1 times -1, which is 0.8. Its expected value is positive because it ends up in the winning state more often. To calculate v of s1, we need to take into account both v of s2 and v of s3, since they are both possible next states. But it's still simple since the rewards at s2 and s3 are both 0. So it's just the weighted average of v of s2 and v of s3, which gives us 0.09. It's slightly positive because we have an equal chance of landing in s2 or s3, but once we are in s3, we have a higher chance of going to s5 than we do the other path, going from s2 to s4. In this next example, we're going to look at a simpler state diagram, but with more complex probabilities. This will be a somewhat more realistic scenario, so you can actually picture what's happening. The start state is your standing. Now someone throws a ball at you, so you can kind of think of this as dodgeball. You have two choices. You can either decide to jump or duck. Those are your two actions. The next state is you either get hit or you don't get hit, which means you're safe. Let's say the reward for getting hit is -1 and the reward for not getting hit is 0. Importantly though, you can see why these state diagrams are somewhat oversimplistic. In particular, when you look at a tree like this, you think, as I mentioned earlier, that the action is to go to the next state. But that doesn't include all the components of an MDP, and so you can see how that doesn't work in this scenario. I can't just choose don't get hit. Similarly in life, I can't simply choose that I want to be rich. I do some actions, and the next state is going to be somewhat probabilistic. I may start a company, and it may fail, or it may succeed, but I can't decide that. All I can do is do the action. The state that I end up in is probabilistic. So to continue on with this example, let's use these probabilities. The probability of jumping, given that you're in the start state, is 0.5. Probability of ducking is also 0.5. Next, we have the state transition probabilities. So the probability of getting hit and getting a reward of -1, given that you jumped, is 0.8. Probability of getting hit and a reward of 0, given that you jumped, is 0. Probability that you don't get hit and the reward is -1 is also 0. And the probability that you don't get hit and the reward is 0, given that you jumped, is 0.2. Notice how I define the probability distribution over the reward, even though I didn't have to. I just wanted to show you the full picture for what the probability space looks like. Notice how you can put in any other number for the reward and the probability is 0, as per the specifications of the problem. So for example, the probability that the reward is 10 is 0, because that just doesn't exist in this game. We can of course just marginalize these to get rid of the reward completely, since it is deterministic. We've already stated that when you get hit, that counts as a reward of -1, and if you don't get hit, it's 0. So if you want to try to solve the rest of the problem yourself on paper, please take this opportunity to do so. So as usual, the value for the terminal states is 0. So whether you get hit or you don't get hit, the value is 0. It's calculating v-start that's more challenging for this problem. So I've started using some typesetting for this equation, since now things are starting to look a little more complicated. But it's still a little simpler than the full Bellman equation because we don't need to consider the value function for the next state. For this type of thing, it's useful to do a little sanity check. We see a summation inside another summation. In code, you can think of this as a for loop inside another for loop, or in other words, a nested for loop. So in the outer loop, we have two things to sum over, and in the inner loop, we have another two things to sum over. And we know that the number of times things run in total is the size of the outer loop times the size of the inner loop. So in total, we should have 4 things to sum over. On this slide, I'm showing you the exact terms we have to sum over. In order to make things fit on this slide, we have to abbreviate some things. So we already know we're conditioning on the start state, so let's just not show that. we know that we're going to either jump or duck, so we can use the letter J or D, which doesn't interfere with any other letter. And so you see that we end up with 4 terms. The first 2 are if we decide to jump. We're either safe and we get 0 reward, or we get hit and we get a reward of -1. The next 2 are if we decide to duck. We're either safe and we get a reward of 0, or we get hit and we get a reward of -1. I'm not going to bother plugging in the numbers here, since the main point of this exercise is how to set up the problem, but you're welcome to do that as an exercise if you want. So at this point, I think any state diagram shaped like a tree is going to be too easy for you. I think by now you understand that this is recursive. Essentially, you work backwards from the end, so the terminal state is 0. The state next to that is whatever reward I get for ending the game, and so on, using the Bellman equation. In this next and final example, we're going to do something even more complex. We're going to introduce a cycle. When there's a cycle, it's not possible to just work backwards because there's no notion of backwards. You can just end up in the same place you started. In this example, we're going to have just 3 states, S1, S2, and S3. S3 is a terminal state, so once you reach it, you're done the game and you get a reward of 1. S1 and S2 are non-terminal states. They can both go to each other, so there's no notion of a starting position. Only S2 can go to S3, but S1 can go back to itself. Let's assume that the only probabilities here are the actions, and that the actions are simply to go to whatever state is next. As we discussed, the actions realistically don't have to be choosing which state is next, but it helps to simplify the picture in terms of what probabilities we have to consider. So how can we solve this problem? Well, we can't use the method of just working backwards like we did previously. That's because of this cycle we have. So the only thing we can do is apply Bellman's equation in terms of the variables involved, and just see what that gives us. Let's do v of S1 first. Using the Bellman equation, we can see that it's equal to P of S1 given S1 times R1 plus gamma times V of S1. So that's the loop just back to itself. And then there's P of S2 given S1 times R2 plus gamma times V of S2. That's the loop going from S1 to S2. Notice that V of S3 doesn't appear here because we can't get to S3 from S1. Let's do V of S2 next. Using the Bellman equation, we can see that there's one term involving P of S1 given S2, and there's one term involving P of S3 given S2. So these correspond to going to S1 from S2 and going to S3 from S2. Notice that V of S2 doesn't appear here because S2 can't go back to itself. And finally, for S3, we know that this is just 0 because it's a terminal state. Now, if we look at these 3 equations very carefully, what do we see? Well, we can see that it's actually a system of linear equations, just like we used to study in linear algebra. We have 3 equations and 3 unknowns. So either we could solve this by substitution, or we could use the matrix method. So if you want to try that on your own right now, please take this opportunity to do so. The first thing we can do is make this more like a system of linear equations by grouping together like terms and spacing them out appropriately. So we can see that we can neatly separate this equation into 3 parts. A vector containing v of S1, v of S2, and v of S3, a 3 by 3 matrix to multiply it by, and a length 3 vector of numbers that just sits by itself. This of course takes the form of ax equals b, and we can solve it using the numpy function np.linealg.solve. As you recall from my numpy prerequisites course, you'd never want to solve this using the inverse method, which would be to calculate the inverse of A and multiply that by B, since that's not efficient in code. The result, if you want to try to calculate it yourself, is V of S1 equals 0.293, V of S2 equals 0.498, and V of S3 equals 0. As an exercise, you might also want to check if these are correct by plugging them back into the original equations. So I hope this lecture gave you an idea of how the Bellman equation can be reasoned about and used. We've seen that for some simple cases, solving for the value function is no more than just working backwards in a tree. We've also seen that for slightly more complex cases, that approach doesn't work, but the Bellman equation is general enough such that it can still represent them. We just need slightly more sophisticated techniques to solve them. And just to give you a big picture view of the rest of this course, the rest of this course is completely and 100% devoted to just one thing: how to solve the Bellman equation. From a bird's eye view, that's what reinforcement learning is. Just like regular supervised machine learning, you want to get away from this idea that you need to do an example on a finance data set, and then you need to do an example on some health data, then you need to work with some house price data, and so on. We know that all data is the same, and what the algorithm sees is just a table of numbers. The real work is figuring out how the algorithm works and coding it. So the rest of this course is devoted to just that. In this lecture, I hope to give you a sense that what we need to solve for the value function is really a better algorithm. We saw that the idea of creating a linear system of equations and then calling np.linalg.solve was pretty general, but we know that that's not a scalable solution. So the rest of this course is going to answer, what are scalable solutions to this problem? What assumptions do they make? And what are their advantages and disadvantages?